Welcome to this first session. Okay, so this is really a warm-up because the week is going to be a bit dense and you're going to hear about so many different things that somehow connect to each other in different ways. And I'm going to give you an overview of the first building blocks of how we measure the expansion of the universe, why we're doing that, why it's important, and why there is a crisis in cosmology. So we'll try to introduce all these points in the first session. So this is the outline of this session. We're going to introduce the Hubble Constant, H0. And then I'm going to present two different ways, very independent ways to measure H0. And then we're going to talk about the Cepheid supernovae distance ladder. And then we're going to talk about systematics and why it's important to control the systematics. And then briefly, I'm going to introduce another type 2 distance ladder, and then some conclusions and perspectives. All right, so let's get into it. So the Hubble constant. So what you can see here is the Hubble Ultra Deep Field. So it's a picture taken by the Hubble Space Telescope when the shutter was left open for many, many hours. If some of you are familiar with photography, you know that if you do a long exposure, you get more light. So this is the Hubble Space Telescope pointing into a very tiny area in the sky that apparently looks empty or dark, but if you leave the shutter open for long enough, then you get some more light from very far away galaxies, and this is what you get. And today we're very lucky to have access to these images and to very powerful telescopes, not only the Hubble Space Telescope, but also the James Webb Space Telescope that's even more sensitive. And today we know a lot about what's going on in the universe. Of course, we still have questions. That's why we're here. But I just wanted to mention that a long time ago, not even a long time ago, like 100 years ago, we didn't know any of that. And the one question that astronomers were trying to answer was, are there different galaxies in the universe? Is the universe limited to the Milky Way? Like, we had no idea where we were, what the universe was made of, how many, like the scale of the universe, the contents, and the nature of things. So this is just to say that this image just reminds me that we have made so much progress over the last decades, and what we know today of the universe is really, really powerful and really impressive, and we should be proud of it. So let's go back a couple decades ago and talk about the discovery of the expanding universe. So as I was saying, in the 1920s, there was a great debate between Shapley and Curtis, and the debate was that they were observing some regions in the sky that they called the nebulae, the spiral nebulae, but back then, like 100 years ago, even the term galaxy was not so common, and we didn't know what a galaxy was, so they were discussing this, and the key to answer this question, of course, was to measure distances. The best way to understand where we are and what are the objects in the sky that we see is to measure how far they are. And during this week, you're going to hear a lot about how we measure distances and why this is so important. So Edwin Hubble was probably one of the most influential scientists at that time because he was able to answer this question and put an end to the great debate. He found that these spiral nebulae in the sky were actually outside the Milky Way. So the universe was not made of just one big galaxy, but multiple galaxies. So this was just the beginning of us understanding what's going on out there. And he did that by measuring distances. And he also made another discovery. He made a plot with distances versus velocity of the galaxies, and he realized that the escape velocity, or the speed of the galaxies that he was observing, was proportional to their distance. And that basically means that the universe is expanding. Now, this is the original figure that he published in his paper in 1929. Here, so let's let's see how he measured that. The velocities of these galaxies were obtained by redshift. So I'll just assume you guys know what redshift is. And it's basically so it's basically from this equation. He was measuring the spectra of these galaxies and seeing how redshifted they were. And now, most importantly, the distances. This is the trickiest point. Here on Earth, you might think distances are not a big deal. You want to measure how far something is. You just walk there, and then you measure how far you walked, and then you get the distance. In astronomy, this is very, very difficult, and people often say that measuring astronomical distances is probably the most difficult thing to measure in astronomy. So to measure distances, we're going to use standard candles. Standard candles are stars or objects in the sky that we know how bright they should be or how bright they are. And by comparing how bright they should be to how bright they appear to us in the telescopes, then you get access to the distance. So this is going to be discussed during this session. And then using this figure, velocity versus distances, then the slope of these points is just h0, the Hubble constant. It's the expansion rate of the universe. So let's try to really picture what it means. Expansion doesn't mean that galaxies really move away from each other, but it's rather space itself that is expanding. So you often hear about this analogy with the bread and the raisin bread. You have the raisin, they don't really move on the bread, but it's just the bread in the oven that is inflating or expanding, getting bigger, so the raisins on it will move away from each other because the bread is getting bigger. So for the universe is very similar. Now, let's talk a little bit about the fates of the universe. So we know the universe is expanding, and the expansion rate is h0, the Hubble constant. Let's compare the fate of the universe with this experiment. Let's imagine you have a cannonball that you throw from the Earth, from a mountain, and you have different configurations, like A or B, means that either the ball is thrown with a very low velocity, or the Earth is very massive that it retains the ball and it cannot escape. And in the case of the universe, so it means that basically the gravitational pull of the Earth is too strong and it wins. The other case is in green, the C or D. So the speed is higher and the mass is not that important, so the ball would go further away. And in case E, in red, the escape velocity is reached, which means the ball goes fast enough, and simultaneously the Earth is not massive enough to retain the ball. So velocity or energy wins. So now let's get back to the universe. The equivalent would be A and B would mean that the universe is massive, and its own gravity will put it back together. And in the case of E, for the universe, it would mean that the expansion is more powerful than gravity. So today we know this is because of the presence of dark energy that is producing this accelerated expansion. So this is basically the equivalent. So let's take this like this. So we have past, present, and future. The first configuration would be very massive universe, and it's rapidly decelerating. You have the Big Bang in the past, and then the big people call it the big crunch, where everything collapses back together. So here, really, the mass of the universe would be dominating. The other configuration would be the universe is a little bit less massive, so it would keep expanding, but it would decelerate. And another possibility is it has been decelerating at first, and now it's accelerating, which means It's dominated not by the mass and the gravity, but rather by dark energy and accelerated expansion. So now let's just do a quick survey. What do you think is the current scenario? Show of hands if you vote for the first one. Okay, who thinks it's the second one? Less massive, slowly decelerating. And who thinks it's the decelerating and then accelerating universe? The third one? Yeah. So it's the last one. And this is actually quite recent, only maybe 25 years ago, 27 years ago, that was discovered that in addition to being expanding, the universe is also accelerating its expansion. So this was discovered in 1998, and it corresponds in the equations of cosmology, in the equation of state, it corresponds to a cosmological constant that is positive. The term is lambda, and it corresponds to the dark energy term. So this is a quite recent discovery. We were just talking about Edwin Hubble, and now we're talking about modern scientists that are still alive and still working hard. So I think it's really interesting to see that the field is really active, and over the last 100 years, we're still working on the same questions and the same objects. So I don't know, this is just very interesting, a very active field. So this accelerating expansion was discovered by both the Supernovae Cosmology Project and the High-Z Supernovae Search Team with Adam Rees, Sol Perlmutter, and Brian Schmidt. And basically, they used type 1a supernovae to measure that the expansion of the universe was accelerating. So we're going to get back to that, but because this is the first session, I wanted to briefly introduce that. And the point here is really to repeat these concepts. So this is the first time we're talking about supernovae, but UK is going to do a whole lecture on that on Wednesday, I think. So supernovae are standard candles. They're distance indicators, very powerful, very precise. And it comes from the explosion of a white dwarf in the binary system, from the accretion of matter from a companion. And basically what astronomers do is that they measure the light curve. So they do a survey of the sky, and suddenly one star would be extremely bright. And then the luminosity would slowly decrease. And by following up this decrease and the peak luminosity, these are examples of supernovae light curves. By looking at the peak luminosity and the shape and the decrease rate, UK is going to explain this much better than me, but, and also a color term and different things that you can use, then you can estimate the distance to these supernovae. And the advantage of the supernovae 1a is that they're extremely bright, and they're some of the brightest distance indicators. So we're going to talk about many different methods, and some of them are fainter and can be used very close to us only, and some other methods can be combined with the first ones and can reach further away. So that's the whole point of the distance ladder. So anyway, using supernovae 1a, which is a subclass of supernovae, these two teams discovered the accelerated expansion of the universe. So let's get back to this. I just wanted to point out that the yellow squares represent really the present. Here's the past and here's the future. But what we want to talk about today is really the Hubble constant, so H0. And H0 means H today. Today is 0. When you see 0, it means the present time. So expansion history at any time or any redshift would be h of t, and the Hubble constant is really h0. So we're not looking at the accelerated expansion over there. Sorry, I'm not using the pointer. It's not very convenient because it blurs the rest. But yeah, so we're going to use only the present time for this school. We're going to use only h0 and not think about accelerated expansion or anything. So this is h0. Now, since Edwin Hubble discovered the expansion of the universe, people have tried to measure how fast it's expanding today and how much is this value of the Hubble constant. And a lot of different values have been obtained. So this is the date on the x-axis, and these first values were around 500. We're going to get back to this, but I want to just tell you or ask you why you think they were so overestimated. But after I give you the introduction, maybe you have your own idea of why the first values were so high. And then more recently, the values went down to below 100. And if you zoom in here, you see something interesting. So instead of being 500, the values were scattered between 50 and 100. And the different symbols here show different teams. And even in the past, something that really arose in the past was that different teams were fighting against each other with different values. And I don't exactly remember who did what, but there was one team that was rooting for a value of 50, and then the other team was really rooting for a value of 100, and then other measurements in between, of course. But this was, I would say, a preliminary debate or tension. Of course, the uncertainties were much higher than today. This was like 30 years ago. But yeah, just to say that people were already arguing between two values, between 50 and 100. Now, the Hubble constant, of course, you already have an idea of why it's so important and why it's so debated today. And it's a really heated topic. But it's also extremely important for cosmologists because it tells us the age of the universe. Basically, the inverse of the Hubble constant gives the age of the universe. So if we take Edwin Hubble's first measurement with about 500 kilometers per second per megaparsec, sorry, I should have mentioned that, but the units, I'm not going to repeat that every time, but the unit of h0 is kilometer per second, which is a speed, per megaparsec, so expansion rate. So yeah, if you take that value 500, then it gives an age of the universe of about 2 gigayears. Well, we know really well that today this is not the case and the universe is much older. So now let's look at the two most debated values. So from two different methods, people get 73 or 67. I'll tell you more about that later. But basically, between these two values, the age of the universe would be either 13.4 gigayears or 14.6 gigayears. And this could make quite a big difference because some objects in the universe can have their age that would be older than one of the values. So measuring how old objects are, like globular clusters or the oldest galaxy, the oldest stars, can also tell us a lot about the age of the universe and cosmology. So I think we all agree that h0 is really a fundamental parameter for cosmologists. Now let's move on to the second point. So there are two ways to measure or infer h0, and this is really the root of the Hubble tension, and we'll get into that. So let's first distinguish measurements made in the early universe and in the late universe. The first way to measure or infer h0 is to use the measurement of the cosmic microwave background, and more specifically the temperature fluctuations. This is a map measured by the Planck collaboration, which is a European Space Agency mission. And this is really measured in the very early universe. Of course, I was saying that h0 is the expansion rate of the universe today. So how do we get a value today if we measure something in the past? Well, we use what's called the Lambda-CDM model, which is the model that describes best what's in the universe, how it behaves. So the main components, dark energy, dark matter, and ordinary matter with these proportions. It describes the evolution of the universe and the formation of structures. So using that model to describe the universe, And combining that with the cosmic microwave background, we predict not only H0, but the whole expansion history, so H of Z, H of redshift. And then taking it at time 0 today, we get a prediction of H0. So I like to remind that it's not exactly a measurement, it's a measurement of the CMB, and then we infer, we predict what H0 is. As opposed to the second method, which is really a direct measurement, and it is placed here in the late universe. This is going to be the distance ladder, so distance measurements combined with redshifts. This is the second method. It is completely model-free, so we do not assume the Lambda-CDM model. We do everything empirically with telescopes, and we measure how bright objects are and many different things. But this is everything that goes there in this measurement is what we see, what we observe, and nothing is assumed. And this is a pretty big difference. You'll see why. Today, what we call the Hubble tension is the difference between the two values obtained with these two different methods. So why is it so? Sorry. Another way to see it is with this plot. We have, so it's reversed. Now you have the Big Bang here, the past, and today is on the left. So really the CMB measurement, again, is made in the past, in the early universe, assuming Lambda-CDM to trace that line and infer the point that is right here in the present time. And on the other hand, the late universe method, the distance ladder and the distance measurement is really made in the present time. So we're not looking back in time. We're not looking in the early universe. We're looking today. Now, here are the most recent values for the CMB and Lambda-CDM technique. The value of H0 would be 67.4 plus minus 0.5 with a remarkable precision. This has really been improved thanks to the Planck mission again. And now in red, the late universe method, the most precise value was recently obtained by the Schu's team, and it's 73.17 plus minus 0.8. And as you can see now within the error bars, they are really not compatible anymore. And this is what is concerning. So now, why is it concerning? Why should we worry about that? Because as you can see, there are three ingredients in these two measurements. There's the CMB, there's the Lambda-CDM model, and there are distance measurements and redshifts. So if the two values disagree, it means that there's something wrong, because there's only one value for the expansion rate of the universe. So there are three scenarios. Either there's an issue in the CMB measurement in the map. We don't think that's the case. Earlier, there was the Kobe satellite, which measured the cosmic microwave background. Then a decade later, the WMAP satellite that produced this second map of the sky. And then the Planck mission that really settled everything and confirmed a lower value of 67 plus minus 0.5. This is not just the Planck mission, but it has also been confirmed and cross-checked with independent missions and telescopes and facilities. There's, for example, the SPT, the South Pole Telescope. Of course, I don't think they have reproduced the whole sky, but they picked some patches of the sky and they tried to measure that, the same thing. And they really confirmed that it was consistent with Planck. There's also the ACT measurement, the ACT experiment, which is in Atacama in Chile. And they were also independent from Planck, and they also confirmed the lower value. So again, this is not just Planck, this is the whole CMB measurement, and it seems to be consistent. The other possibility is that there's an issue in distance measurement or the distance ladder. And today, Teresa and I are going to try to convince you that it's not the case and that we're doing everything correctly and we haven't missed anything. Now, if we are so sure that the CMB is not the issue and distance measurements are correct, the only other option is that there's an issue with the Lambda-CDM model. And that would be a breakthrough. That would be very concerning because everything we describe in the universe fits really well with Lambda-CDM. And so far, it's been very good at describing what we see. And we haven't found anything better than Lambda-CDM. So having to change it or adjust it would need a lot of work. And if you look at the archive, there are about many different papers every day trying to change Lambda-CDM and bring new physics with new particles or exotic dark energy, trying to fix this issue of the Hubble tension. Unfortunately, it's been harder than we expected, and unfortunately, when you fix something, you break something else. So the theorists are having a really hard time with this, but yeah, this is why we're all here trying to understand what could be wrong and not only fix Lambda-CDM, but also dig into the measurement and try to see if we have missed something, reproduce the data, look at the data together, and that's exactly what we're here for today. All right, so I've talked about two specific methods, but the Hubble tension is not just a disagreement between two methods or two teams. It's not just Planck versus Shoes. It's really a global disagreement that seems to be confirmed between early universe values versus late universe measurements. So that's something to keep in mind. Now we're going to go into the distance measurements. And this is exactly the expertise of most of the speakers that we have this week. So I'm going to do a first introduction, but believe me, you're going to hear a lot more about the distance ladder this week. First, let's start with the basics, measuring distances on Earth. If you're on Earth, things are really easy. You have a method that's called the parallax that you can use on Earth. You want to measure the distance to a tree that's across the river, and then you just look at it from an angle, and then you move just a few meters, and then from how much the tree has moved in your field of view, from which angle it appears different, you can derive how far it is. This is a very simple technique that's, we call this a geometric technique, and you'll see it can also be applied in space. Another way to see that is the lighthouse technique. The sailors at sea, they know how bright a lighthouse should be. So if they see a lighthouse that seems very faint, they know they're far enough. And if they see it very bright, they know they're too close to the shore. And in astronomy and even on Earth, it's the same. The brightness follows the inverse square law, so it decreases like 1 over distance square. So an object that's twice further away will be 4 times fainter. And then I really like this, this image. This technique is what I call objects of known sizes. So the bird and the plane appear like they are the same size on the picture, but because you know that a bird is much smaller than a plane, you know that the plane is much further away. The plane is much further away than the bird, but that's only because you know what a bird and a plane look like. But in space, you have galaxies, stars, and objects. The thing is, you don't know how big they should be. Well, sometimes you do, and that's how you measure their distances. So these are 3 methods that we can really understand quite easily on Earth, and that leads me to applying these same techniques in space. First, let's look at the parallax technique. So to measure distances in space, of course, you need a much larger baseline. So just moving across the river doesn't really tell you much about how far a star is. So you would have to use bigger baselines. And we can do that easily by just using the movement of the Earth around the sun. If you look at this star here, bright star, during, for example, winter in December, you will see it here. And behind that, you have background stars that don't really appear to move or to change their pattern. They are at the same position. But then after 6 months, in summer, the same bright star that's in front of you will be in a different position, at a different position compared to the background stars. And exactly that angle would give you how far the star is. So the further away, the smaller would be this, this motion. And this is exactly what the Gaia satellite is doing. This has been launched about 15 years ago when I was doing my master's degree. And the ESA Gaia satellite is dedicated to measure astrometry. Astrometry means positions of objects in the sky, their distances, and also their proper motion. So it's dedicated to measure these quantities for billions of stars, mostly in the Milky Way, but also further away, also in the Magellanic Clouds and a little bit further. I don't know how good you can see that, but it's supposed to be moving. You have the Milky Way in the background, and then you have some stars moving. And this explains, in my opinion, this really shows what the parallax means. So, for example, let's take this one. There's a bright star that's making circles, and this really shows that it has a large movement. And this would tell you that the star is really close to you. And if you look at another star that's moving with a very tiny motion, it means that it's further away. So that's basically what Gaia would see through its detector. What Gaia is measuring is a combination of both the proper motion of a star and its parallax. So Gaia is not on Earth, it's at the Lagrange point number 2, so it's a stabilized point in space. So it would observe a star during different time of the year, and this would be the blue points, and then the Gaia team will reduce the data and trace this green shape. And by the shape of this, we would obtain the parallax measurement. So the bigger this loop, the wider this loop, the closer the star would be. So the proper motions, the movement of the star in the sky would be in that direction, and just the parallax would be the circle. So it's a combination of both. So that was the parallax in space. Now let's look at objects of known size. So objects of known sizes, there's one example that, of how we can do that in astronomy is using eclipsing binaries. So basically we use a system of 2 stars that are orbiting each other, and we can model the orbits of these 2 stars. This is a method that's particularly useful in the Magellanic Cloud. So if you're not familiar with this, LMC and SMC, we're going to be talking a lot about these 2 galaxies. It's the large Magellanic Cloud and the small Magellanic Cloud. They are the closest galaxies to the Milky Way. They're much smaller. They're dwarf galaxies. But because they're really nearby, they're really the next step. Like the Gaia parallaxes, they work really well in our galaxy, in the Milky Way. But then going to these dwarf galaxies nearby, parallaxes from Gaia are not good enough. So you have to rely on other techniques, and that's how eclipsing binaries are really helpful. So what astronomers do is that they follow these systems of stars very regularly, like every night with the same telescopes, and they model the light curve. So you see the different peaks here, which are the eclipse when the other star passes in front of the other. And they also model the radial velocity curve, and this is the trickiest part because you need a powerful telescope to get a spectra and see basically how each component is moving and in which direction. So by modeling this system, you can infer how close they are from each other, so the separation of these two stars. You can also infer the mass of the system and the radii. And most importantly, you get the distance of that system. It's a really powerful technique. You get extremely precise and accurate distances from eclipsing binaries, but it requires a lot of observing time. And you need very sensitive telescopes. You need both photometry and spectroscopy. So it's quite challenging, but it's been extremely helpful. Now, let's get to the lighthouses in space. And we have what we call standard candles, which means just like the lighthouse, we know how bright stars should be, theoretically. And then we just compare how bright they look in the sky. The first one, my favorite, Cepheid variable stars. They are just pulsating because of some instability in their atmosphere, and there's a layer that becomes thicker and prevents the light from escaping, and then the stars becomes hotter and expands, and then there's an equilibrium that makes the star pulsate. It's very regular. What is really important with Cepheids and how they are standard candles is because they follow a period luminosity relation, and you're going to hear a lot about period luminosity relations. I might call it PL relation for simplicity, but because this is a summer school and you're maybe not familiar with that, I'll try to keep calling it the period luminosity relation so you don't get confused. So how they are measured, it's the same as eclipsing binaries. You need to follow up every night and observe many different points first to get a light curve that would look like this for a Cepheid. So the brightness is just varying. The pulsation could be between a couple days to 100 days, but it's always the same. So the short period Cepheids are here on this side, and they have the fastest pulsation. They have periods of about a few days. And then the brightest Cepheids have a slower pulsation, and they're on this side of the relationship. But the period luminosity relation of Cepheids is really tight. It's well understood, and it's been used for decades, and even for now a century since Edwin Hubble used it to measure the first estimate of the Hubble constant, the expansion rate of the universe. So that's really how Cepheids work, through the period luminosity relation. The other standard candle that we'll be talking about this week is type 1a supernovae that are, as I said, it's an explosion of a white dwarf accreting materia from another star nearby, and you have these light curves. So there are many others, other methods, other standard candles. I call these two standard because I think it's safe to say it. They are standard. We know how bright they should be. We measure how bright they are. Comparing the two gives the distance. Other methods are still under development. They are sometimes called standardizable candles because we're still trying to standardize them. So we know they follow some rules or some pattern to tell us the distance, but they might depend on some parameters like dust, color, metallicity, and you need to account for these dependencies, and that would be what we call systematics. So, of course, Cepheids and type 1a supernovae also have systematics, but they are, I would say, very well understood and under control. So we're going to combine the two. Cepheids are, however, fainter. So we observe them in the Milky Way, in the Magellanic Cloud, and up to some distances in some galaxies relatively nearby. But it's quite hard to use only Cepheids to trace the expansion of the universe, because to trace the expansion of the universe, you would have to go further away to really reach the regime where galaxies are moving away from each other and they're not dominated by local gravitational interactions. And for that, you need to go further away than just what Cepheids can measure. At some point, they are too faint to really give you a good precision on distances. So you have to use something else, and that's why we introduce supernovae, because they're much brighter. So the distance ladder is really the combination of these two methods. Oh, that was just a little video. I don't know if you can see it really well, but it's just a view of a galaxy, I think, or a cluster with stars blinking. And this is just a cute way to remind you what we astronomers do every day is just look at the blinking sky, either for Cepheids or supernovae. We look at a patch in the galaxy or in the sky and variations of light. Like you have in the background the stars that stay the same. They're as bright. They're the same brightness all the time. And then you have our favorite stars, the Cepheids and the supernovae that would blink or become brighter and then get fainter again. And the Cepheids that are constantly blinking. And that's what we're looking for. All right. So now, combining all that to do the distance ladder. The first rung, or the first step, I'm going to be talking about rungs. So first rung, second rung, third rung. The first rung is to use geometric distances, basically what we have just discussed, to calibrate or establish the absolute scale of the Cepheid period luminosity relation. And for that, we use 4 galaxies, and we will call them the anchor galaxies, because they really anchor the rest of the distance ladder. For that, we use 4 anchor galaxies, the Milky Way with Gaia parallaxes of Cepheids. In the large and small Magellanic Clouds, we use eclipsing binaries that I just described. And then there's a 4th galaxy a little bit further away, NGC 4258, that is very interesting because it has a maser in its center. Well, I'm not an expert on that, but it's basically the motion of that, the masers around the center can be modeled. And it's also, again, a very geometric method. Through the Keplerian motion of the masers, you can infer the distance to this galaxy. Unfortunately, we only have this one, and it's hard to get others like that because it's very special, and the inclination of it is very convenient. But it's hard to find others like that. Now, in these 4 anchor galaxies, we establish the period luminosity relation. We could also just use one. You can also just use the Milky Way, or even in the past, like 20 years ago, people were just using the Large Magellanic Cloud as only anchor, and it works just as well. But now we have good geometric distances through eclipsing binaries and the maser and Gaia, so we combine those to have a more powerful and more robust calibration of Cepheids. Once we have this calibration of Cepheids, we move on to the second rung, where we have both at the same time in the same galaxies. You have Cepheids, they're still bright enough so that you can observe them. And you also have type 1a supernovae. So using the Cepheid distances, we establish the absolute scale of type 1a supernovae brightness. So this is quite tricky because you need to have both in the same galaxies. And it's really limited to the volume where you can still see the Cepheids, but also have supernovae. And supernovae 1a are not so common. It's really rare. There's about 1 per galaxy exploding every century. So it's not so easy to have many galaxies for that second run sample. But we have 42 supernovae in 37 hosts, so it's quite good. Some galaxies have even 2, up to 3 supernovae. So there's been a lot of work in this step recently. And then finally, we go even further. At this point, we don't even see the Cepheids anymore. They're too faint. But fortunately, we see the supernovae because they're bright enough. And comparing their distance to their redshift gives you the Hubble constant. So that's, as you can see, it's purely empirical geometry, Cepheids, supernovae, and you get distances and you get a cosmological parameter. As I said, you want to go far enough to avoid local gravitational interactions, because when you look too close, like nearby galaxies, they're interacting a lot, they have very high proper motion, and you don't really see them expanding, but you have to go further away to see the actual expansion. But you also want to stay close enough that you're observing H0, Because if you go too far, then you're observing h of z, h of another redshift that's in the past, and it's not today. So that's why the Hubble constant is really measured between approximately redshift 0.02 and 0.2. Maybe my colleagues can correct me, but you'll go to higher redshift during the rest of the week, and you'll see how supernovae work at this distance. Something that's important that I wanted to mention is that the Cepheids on the first and second rung, basically every Cepheid in that method, are observed with the Hubble Space Telescope. And why is it important? Is because if you use different telescopes, or even the same telescope but different cameras or different instruments, then you introduce systematics. You introduce photometric inhomogeneity. And having really everything on the same system with the same filters and the same instrument ensures that everything is clean and you're observing it within the same system with the same conventions. And this is the reason why we have been able to reduce the uncertainties on the Hubble constant. Just using a different telescope or combining two systems would significantly increase the uncertainties. So this is an important point. Okay, so you have another way of seeing this, the distance ladder. Really keep in mind the 3 steps, the 3 rungs with geometry. There's only parallax. But you know there are 4 anchor galaxies and other methods. And then supernovae hosts in the second rung, and then redshifts and supernovae in the last step. The other way to see this is with this plot that you probably will see again during this week. This was from the SHOES team from RIS 2024. And it's basically the same as I just showed in the cartoon version, but it's what we show in the paper. You have the independent geometric methods to calibrate the Cepheids. Then you have the supernovae calibrators. Here I wanted to point out that we have done or they have done a huge amount of work to double recently the number of supernovae on the second step. Just 10 years ago, about 10 years ago, we had only half that number. I think we had 19, and now we have 42. So this has been really a huge step in improving the precision of the Hubble constant. And finally, the last rung with supernovae, this has been standardized very cleanly by the Pantheon team, Pantheon Plus, to ensure everything again is on the same system and they're not introducing any systematics. So we connect these 3 steps together, and we use the near-infrared and colors to minimize the impact of dust. If you only work in the optical filters, then you're really affected by dust. But if you look into the infrared, then you can limit the effect of dust. And we do a simultaneous fit of these 3 steps with 5 free parameters: the Cepheid and type 1a supernovae luminosity, the slope of the period luminosity relation, gamma, which is the metallicity dependence of Cepheids. This used to be the main systematic of Cepheids. And then finally, 5 log H0. And this has been the result of the SHOES team as of 2022. Again, the higher value, 73 plus minus 1. And this is why you should trust us. I would say the SHOES team has published more than 40 papers in journals with really high number of combined citations. We have used more than 1,000 orbits of the Hubble Space Telescope with over 20 accepted proposals, and this has been a tremendous amount of work. And also I wanted to mention that the data is public. So why do we talk about this distance ladder from Cepheid and supernovae so much? Because it's been so far the best that we could do. It's been the most precise. Why? Because Cepheids and supernovae have the best understood physics. We know exactly how they work from the physics point of view compared to other methods. Again, we have used homogeneous observations with the same telescope. Again, this is very important. And also, we have worked hard over the last 10 years to really populate these 3 rungs with a lot more objects. So adding more anchor galaxies, adding more supernovae hosts to really make this distance ladder more robust. So now let's talk a little bit about the systematics. This is how the distance ladder works. And over the years, we have received concerns and complaints that, oh, there might be issues, or there might be something that we haven't estimated correctly. So we have looked into the main systematics of the distance ladder. And one of them is the Milky Way calibration. There's Gaia. Gaia works really well since 2021. We have the Gaia data release 3 that's been very accurate, very powerful. But something you should know is that for Cepheids are really bright, and you would not typically think that way, but they're even too bright for astronomers because bright objects would saturate detectors, and bright objects are not the best calibrated. Like, there are many more faint stars in the universe, so Gaia would measure better the faint stars than the bright ones. So Cepheids are treated a little bit differently in Gaia. They require a small corrective term, which we call the Gaia parallax 0 point. It's quite well constrained now, and a lot of people in the Gaia collaboration work on that. But we have been thinking, is there an alternative approach? Because Cepheids are too bright, and we want to do that. We can possibly do that better. So we have developed a technique based on open clusters. We're looking for fainter stars, and open clusters host a lot of fainter stars than Cepheids. So if you find Cepheids in open clusters in the Milky Way, then you average all of the parallaxes of all the members of these clusters. And because they're numerous and they're fainter than Cepheids, then you get a better estimate of their distance. So that's something I have done during my PhD, and also I also continued this work during my postdoc at Johns Hopkins. So we cross-matched catalogs of Cepheids in the Milky Way with catalogs of clusters, and comparing their positions in the sky and also proper motion. This is in pink, the mean proper motion of the cluster, and in blue, the proper motion of the Cepheid. You can establish some memberships, and we have so far a sample of 17 very accurate confirmed membership. We know these Cepheids belong to these clusters. So yeah, that's what I was saying. Clusters are more precise than individual Cepheids. And also because the members are fainter, all of the yellow dots are the members of the clusters. Fainter stars are better calibrated in Gaia, so this is why this works so well. We have 17 cluster Cepheids, and they're as good as the previous 75 individual Cepheids. Because the 75 are very bright, and the 17 cluster Cepheids use the mean parallax of the members. So we have observed them again with the Hubble Space Telescope to make sure everything again is consistent in the same system. And this is a period luminosity relation for Cepheids, individual Cepheids in gray, and cluster Cepheids in red. So if you're not used to looking at a period luminosity relation every day of your life, you might not find it outstanding, but I do find it outstanding. The dispersion is much better with the clusters, and if you don't see it clearly, you can look at the smaller figure, the inset here, with the precision, the uncertainty, on the parallax. In red, the clusters are way lower, have way smaller uncertainties than the individual Cepheids. Using that, we plug that into the Hubble constant measurement in the distance ladder, and we have been able to reduce the uncertainty. And I wanted to mention that because this is the first time the uncertainty on H0 goes below 1 kilometer per second per megaparsec. So this has been a recent improvement. Now, the second systematic that I wanted to talk about, crowding, used to be highly debated. Crowding is basically contamination from background stars or nearby stars. So this is what you see from both the Hubble Space Telescope and the James Webb Space Telescope in a box where you have a Cepheid in the middle in red, and you have a lot of stars around. With the Hubble Space Telescope, it is hard to distinguish the contribution of the Cepheid from the contribution of the other stars behind. And this is what we call crowding. Now, with the James Webb Space Telescope, the resolution is much better. And what you see would look like this in comparison with Hubble. This time, you can distinguish the stars behind from the Cepheid. So it used to be a systematic. So it's not a typical systematic. It's more a bias that used to be removed. So before having JWST, we only had HST images. So we would do something a little bit tricky. We inject fake stars in the image of known brightness, and we remeasure them to see how much the crowding impacts the measurement. So you're going to hear about this again, I believe. So something you can also, how you can see crowding is by comparing Cepheids in inner regions of some galaxies versus outer regions of galaxies. You can really see the difference. It's much more crowded in the inner regions. And if you plot the period luminosity relation in this galaxy with red stars showing the inner regions and blue stars showing the outer regions, it really shows more scatter, so more uncertainty. So yeah, it used to be corrected with, by injecting artificial stars, but now we have the James Webb Space Telescope. This is an example of the same Cepheid observed with both telescopes. And on the first one, you see there's the Cepheid in the middle, you see a few pixels, and next to it, there's also a couple of pixels that are dark, but you cannot really distinguish if this is a different star and how much it's contributing to the flux. And now with James Webb, you see, okay, this is a different star, and when we do the photometry, you can distinguish the flux from the two stars and have a much cleaner measurement of the Cepheid. This is a period luminosity relation in one of these galaxies with, in gray, the Hubble Space Telescope measurements, and in red, I hope the quality of the screen is good enough for you guys to see, because this is really a really outstanding result that we have obtained recently. In red, this is from James Webb, and the dispersion of the period luminosity relation has been reduced by a factor 2.5. So this has been a really tremendous improvement. But most importantly, the distances agree. So that's what we wanted to reproduce, is to measure the same distances, measure the distances to the same galaxies with both Hubble and James Webb. And what we see is that they agree. So we haven't been able to observe all of the supernovae host galaxies with James Webb because, as you can imagine, it's very expensive and it's very difficult to obtain observing time. But we have observed about half of them, half of the 42. You have here the histogram showing in blue the different supernovae hosts, giving each a different H0 value. And in red are the hosts that we observed with the James Webb Space Telescope. Again, when we're talking about crowding, and later this week when you'll hear about photometry, where you are in this distance ladder is really the second rung. In the first rung, you're not so worried about crowding because you're nearby and you can distinguish stars very well. But it gets trickier when you observe Cepheids in the first supernovae host galaxies, so that's where we are. Now, we have done even better with James Webb. We have found the perfect host, and we even published a paper called The Perfect Host. And this host is very special because it has a spiral galaxy and a tidal companion right next to it. And what's really good is that they both share, of course, the same distance because they're gravitationally bound. But The Cepheids in the spiral galaxy, they look like this in the orange box. It's a little bit crowded. You see there's old population behind. But the tidal host, for some reason, was stripped out of the old population, and it has only young population. So it has technically no background. This is the green box here. And it's a very pure environment where technically you have no background, no contamination whatsoever. So we have found the Cepheids in that tidal companion. They're shown in yellow. And using these Cepheids in the perfect host, we reduce even further, the dispersion of the period luminosity relation in red. And it's a really far away galaxy, but it has the scatter of what you observe in the Magellanic Clouds, really nearby. So it's a very, very exquisite measurement, I would say. And again, it shows great agreement in distances between Hubble Space Telescope measurement and James Webb. So the conclusion of that experiment is that the crowding effect that we were worried about is really not a possible source of the Hubble tension. So people used to think, okay, the images from Hubble are crowded, and that explains why they get a higher value for H0. Now we have been able to prove that it was not the case. So that was a paper that we published 2 years ago by Adam Rees et al. And the conclusion is that, distances agree, but don't get too excited about James Webb because, as I said, it's hard to get observing time. And so far, unfortunately, or fortunately, I don't know, the strongest constraint on H0 is still from the Hubble Space Telescope. James Webb is good, but you need statistics. We don't have as many galaxies observed with James Webb. So far, HST has 42 supernovae hosts, so it's still more precise. Also, H0 strongly depends on the sample of supernovae host galaxies that you use. If you pick only a couple of supernovae hosts, then you might have a bias depending on how you select your sample. And JWST is great, but the sample is not big enough to give any conclusion on the Hubble tension, only from James Webb. All right, so any question? So all these different improvements really give us confidence that we're not missing any unknown or unknown systematic. It reinforces the Hubble tension. It's now, I believe, over 6 sigma significance. And the distance ladder is now extremely robust. It's hard to change something and get a lower value by more than 0.5 lower. So what we're trying, of course, is to keep improving that measurement. It's the one in red, so it's so far the most precise, Cepheids and supernovae. But what we really want to do is refine other methods that are completely independent, that do not rely on Cepheids and supernovae. Because if they're independent, they can tell us a lot about the Hubble tension. So that's why I wanted to mention briefly the type 2 distance ladder. This is something one of our colleagues is involved with at Space Telescope. And this is a completely alternative distance ladder with tip of the red giant branch and surface brightness fluctuations. And this is also a good way to introduce the tip of the red giant branch, because you're going to hear about this a lot again. Surface brightness fluctuation, not so much, but tip of the red giant branch, this is my introduction. So tip of the red giant branch is a method that's different from Cepheids in the sense that you don't need to follow up the same stars and have light curves and time series. You can just shoot one image of the same galaxy one time in 2 filters, and that's it. You have your measurement. You just put all your stars in a color magnitude diagram. You have here on this plot the color on the x-axis and the magnitude, which is the I band, which is optical, on the y-axis. And you should be able to see a discontinuity. The tip of the red giant branch is really this discontinuity, and it corresponds to the brighter ascent of red giant stars before they undergo the helium flash. So he's going to talk about the physics behind this, I believe. So it's really different. It's highly efficient because, again, no time series, just one image, or two filters. And it's not limited to galaxies where you have only young stellar populations like Cepheids. You can really do TRGB, tip of the red giant branch measurement in basically any galaxy. So that's the first step that would replace the Cepheids. And then on the second and third rank, to replace the supernovae, they're using surface brightness fluctuations. Here's an example of 3 different systems. The first one is really close, and then they're further away. And basically, the number of stars per pixel is varying. And the further away you go, the more distant galaxies look smoother. And we're using that as a distance indicator. Again, compared to type 1a supernovae, it's much more efficient because only one epoch, only one observation, and you get your measurement. And so far, they have reached a 4–5% precision with that method. So you remember that plot I was showing earlier with Cepheids and type 1a supernovae? Well, now with that alternative type 2 distance ladder, well, they're still trying to use Gaia on the first rung to calibrate the tip of the red giant branch. And they're also using the maser host with its geometric distance to calibrate the tip of the red giant branch. And then this is what they use instead of Cepheids, and then surface brightness fluctuation to redshift on the last step to measure the Hubble constant. So this is called the TRGB SBF project. Our colleague Gagandeep Anand from Space Telescope is involved in, and they have obtained a lot of JWST time to do that. We're really excited. It's the first promising independent ladder. And what's really good, what they're doing is they're using a single detector for everything. They're using NIRCam on the James Webb Space Telescope to observe both TRGB and SBF. So that's going to be a very clean measurement. All right, so my conclusion is that here's the tension with, in blue, the empirical measurement, and in red, the CMB, Lambda-CDM measurement. This plot only goes to 2023, I believe, but now the tension is really 6 sigma, so even more precise for the blue points. I wanted to point out that the blue points haven't really moved much. They have always been around 73. But since Planck came out, we had a decrease of the red value. I'm not exactly sure why. But yeah, again, the Planck measurement, the red point, have been confirmed with different experiments and measurements. So it's really not just Planck versus distance ladder. It's also been confirmed with parallel distance ladder, type 2 distance ladder. This paper by Newman, 2025, is using only early type supernovae, for example, supernovae hosts. And I think you're going to hear about the distance network. It's a very recent approach that has been developed and published last year. It's the H0 distance network collaboration led by Stefano Casertano and some of the speakers in the room as well, where we combine a lot of different methods very cleanly, and we take into account the covariance between the different methods to get an even more precise value. And now we reach a precision of 0.8. All right, so this was just the introduction. So this is just the overview of how the distance ladder works, how you connect different methods to reach more distant galaxies, and why the Hubble tension is so important, why people are publishing so many papers on the Hubble tension and trying to figure out what is causing it. So now, this is just my last slide. I wanted to come back to the discovery by Edwin Hubble. Now that you've had this overview, do you have a clearer idea of why Hubble had overestimated H0 in his first measurements? Well, the main answer to this question, why did Edwin Hubble measure a H0 value 7 times too high, is because he confused two types of Cepheids. Cepheids are not, well, they're well understood, but they are different types of Cepheids, just like there are different types of supernovae. We're mostly using classical Cepheids, but there are also type 2 Cepheids and other types. They're Cepheids pulsating in first overtone mode, so there are more technicalities. But basically, Edwin Hubble was confusing fundamental Cepheids with type 2 Cepheids. And because they have different brightnesses, he would obtain a much higher value. So that's mostly the reason. Yeah, so that was my conclusion.